All right. So Unit 2, we're going to talk about some things. 2 lessons are going to kind of be related, and then they're going to move on to more calculus stuff. First stuff, asymptotes. You kind of already know about asymptotes. It's not going to be new, but we're going to think about it in a new way. We're going to use limit definitions of asymptotes. We're going to talk about continuity. You probably have an understanding of what continuity is, but we will use limit definitions for continuity, and then we will start to define derivatives, slopes of tangent lines. And that's when we really start talking about calculus concepts. Okay? So it's kind of a one-off unit, a transition unit. After this unit, we just deal with tangent lines for the rest of the semester. All right? An asymptote is a line such that the distance between a curve and the line approaches 0 as they tend to infinity. We're going to work with 2 types. You can see both types in this example. Okay, we have a vertical asymptote, this imaginary line. We can say it's passing through this x-coordinate A. And I'd say I have a vertical asymptote at x equals A. X equals A would be a vertical line. My function is going to be approaching that vertical line, going up to positive infinity from the right, and going down to negative infinity from the left. Then we see we have a horizontal asymptote, this imaginary line, where my function is going to be approaching it as we go to the left on my x-axis. So as I plug in bigger and bigger negative values, I'm going to get function values are going to get closer and closer to this line here. We can say this is at something like B. So that's our horizontal asymptote. We could say it's at the line y equals b. Now let's define these asymptotes using limits. Okay? I'll say when do vertical and horizontal asymptotes occur? We will say that a vertical asymptote occurs when a one-sided limit approaches infinity or trends towards infinity. We'll say approaches, but we also will use equals infinity. It's impossible to equal infinity, positive or negative infinity, but we'll just use that to denote approaching. Okay, so back up to this example. I'll say the limit of this function as x approaches A from the left. So as I'm approaching A from the left, my function values are getting more and more negative. They are approaching what we would consider negative infinity. And if this is f of x, we say of f of x equals negative infinity. And as we are approaching A from the right, my function values are increasing more and more and more. They're not approaching some value, but they are approaching infinity. Miss Wolf, put your phone away. Okay, so that's a vertical asymptote now using a limit definition. A horizontal asymptote will occur when we examine the limits as x approaches infinity. So different. So we're used to finding limits as x approaches a specific value, but now we will be examining limits as x is approaching infinity, positive or negative infinity. So in this example here, I would say we have a horizontal asymptote at y equals b because the limit as x approaches negative infinity of this function is equal to b. As I'm getting further and further to the left with my x's, with my inputs, my function values are getting closer and closer to the value b. Today is all about vertical asymptotes and horizontal asymptotes, just using limit definitions. And we're going to start with dealing with just vertical, and then we'll change over, deal with horizontal. That way you can deal with both. Okay, now you're not used to this, but you will become used to this. The infinity being in the limits next to the x. Okay, and you need to be used to a limit being what we say equal to infinity. Okay, start with vertical asymptotes. Now the key today is we are going to need to figure out how our function is behaving around our vertical asymptote. Okay, whether our function is going to be going up to infinity to the left of a vertical asymptote or down to negative infinity, and then we have to examine the right. Now if we look at this function, negative 2 over x minus 3, we should know that there has to be a vertical asymptote at x equals 3, because I cannot simplify this function using any algebraic technique to get rid of the x minus 3 in the denominator. So immediately I look at that and I say, okay, there's no hole where their limit could exist. We're going to have a situation where no matter what, I can't plug in 3. I have a vertical asymptote at 3. And I'll just denote vertical asymptote with a V and then an A. So I can go ahead on, a sketch of the graph of negative 2 over x minus 3. Just draw an imaginary line through x equals 3. Okay, and I definitely know it has a vertical asymptote at x equals 3 because I can't simplify that like I could with those other limits where we had other functions when we had holes. Okay, but the question is my function going to be going like this to the left of it? Is it going to be trailing down? Is it going to be coming from up there? Is it going to be coming from over there? 4 different options for the way my function behaves around this asymptote. And we're going to try to figure out what's going to happen. Okay? And if I had a calculator and I wanted to do this numerically, it's a piece of cake. I would take some x values and I'd be able to get some function values. And let's say I want to figure out what's going on to the left of this vertical asymptote. Well, that would be finding the limits as x approaches 3 from the left of this function. Well, I could start with a value like 2, and then I could continue to kind of get closer and closer. Maybe I look at 2.9, 2.99, and maybe 2.999. And kind of space these out a little bit better. Okay, and if I wanted to find this limit, well, in this situation I could do this by hand, but in most situations you won't be able to, and you won't have a calculator available. But just if we had a calculator and we could do this by hand, I'd plug in 2. This would be negative 2 over negative 1, and I'd get 2. If I plugged in 2.9, I'd end up with negative 2 over negative 0.1, and I'd get 20. If I plugged in 2.99, I'd get negative 2 over negative 0.01. I'd get 200. And if I plugged in 2.999, I would get negative 2 over negative 0.001, giving me 2,000. And numerically, I can see that as I get closer and closer to this vertical asymptote, but from the left side, my function is going to be increasing. Simple, right? We don't have this luxury though. We won't be able to do this every single time. We won't have calculators available. We won't be able to plug in a value that's really, really close to the left of my value and really, really close to the right. But we're essentially going to be kind of doing that just in our minds algebraically. Okay? But the concept that we're going to use that's going to be crucial is what's going on right here. My numerator is staying the same, and as my denominator gets smaller and smaller, what happens is the product is getting bigger and bigger and bigger. This should make sense. If I take a number and I keep that number the same, but I divide by an ever decreasing number that's getting closer and closer to 0, the resultant product is going to get larger and larger and larger. Take 5 divided by 1, that's 5. 5 divided by 0.1, 50, 5 divided by 0.01, 500, and we get bigger and bigger values, okay? That is the crucial idea behind what we're going to be doing with these vertical asymptotes, is that if you divide anything by something infinitely small, we're going to get something infinitely big. Take a value 5, divide it by something what we'll consider infinitely small. So, and a lot of zeros. I put dot, dot, dot there just to represent a lot of zeros. And what will we get? Something super, super huge. Now, the rules of multiplication and division are still going to apply if this was a negative 5 and this was a positive value that was infinitely small. This would get super huge just in the negative direction. Okay? That's something that we know. A negative divided by a positive is a negative. We'll just confirm that in a second. What we're going to do is we're going to use notation for these infinitely small values. I'm going to use a 0 with a negative sign above it and a 0 with a positive sign above it. Kind of like our one-sided limits. This is like 0 from the left. This is essentially like a negative infinitely small value. And then 0 plus, we will consider a positive infinitely small value. Okay, so we're not going to write this anymore. Instead, I'm just going to say, well, this is negative infinity. Okay? And let's just make sure we're like comfortable with our multiplication rules, our division rules of positive and negatives. So I'm going to say if k is a positive number and our denominator is approaching 0, so it's infinitely small. Now, it could be infinitely small and negative. It could be infinitely small and positive. So remember, this is like negative 0.0001. This is like positive 0.0001. Well, if this is a positive value, could be anything, divided by something infinitely small and negative, it's going to be something infinitely big and negative. Positive divided by something infinitely small and positive, infinitely big and positive. And it's just your rules of division. You know, it's nothing crazy. If you know your rules of division, this should make sense. And you should know the concept. You take a value, divide it by something that gets smaller and smaller and smaller, you get something bigger and bigger and bigger as a product. Okay? Now, let me show you what we're going to do using this kind of notation so that we can examine what's going on around vertical asymptotes. So we are going to evaluate the behavior of a function around a vertical asymptote. The first function we're going to look at is negative 1 over x plus 1. And I should know that this function has a vertical asymptote when x equals negative 1. Why? Because I will never be able to plug in negative 1 into that function. Can't simplify it to get rid of it. It's going to be there for good. So immediately I can just do negative 1, go with that guy. But now we have these limits set up so that we can evaluate the behavior of my function around this vertical asymptote. And this is what I'm going to do. Typically, when I ask to find limits, I just go ahead and plug it in. Right? I always said you should always check your limits by plugging in your value first. And if you're, if you get a defined value, then you win. You don't have to worry about it. Well, I'm going to do the same thing here. I'm going to plug in your value first. Now, typically, we would just plug in negative 1 and realize this is 0 and this is negative 1 over 0, and that's undefined. But I'm going to include the minus sign here. Now, the next couple steps I could do in my mind, okay? And I do in my mind now. For you guys, you're going to probably want to show these next couple steps until you get comfortable with this process. Okay? So I'm going to do this in blue to show you that this is in my brain. What I'm going to do is draw a number line, and I'm going to make sure I understand what a number to the left of -1 is. This says brain. So I'm thinking of a number line. I got 0, -1. -1 from the left would be right there. That would be like -1.0001. Okay, or 0.1. Okay, I got that. That's a good start. The next thing I'm going to do in my brain is, instead of using this -1 from the left, I'm just going to go ahead and replace it with that number. Then I'm going to think to myself, okay, if I take this number and add it to 1, what do I get? Well, I get something really, really close to 0, but it's going to be negative. Why? Because my negative value is bigger than my positive value here. So I'm going to go and say, well, this is like -1 over -0.0001 or something like that. Well, that will allow me to say, oh, this is like -1 over something approaching 0 from the left, something infinitely small and negative, which is telling me, knowing that a constant divided by something infinitely small, and knowing that a negative divided by a negative is a positive, that this function is going to be trending towards infinity to the left of -1. And I go and I can sketch that. So I went from here to here to here to here, which allowed me to do that and write that. Okay, you guys do it with the other one. Let's figure out the limit as x approaches -1 from the right. Go for it. Do your number line. Replace. What do you get? Use your notation. In my brain, I'm thinking, what does it mean to be approaching -1 from the right? Well, that's like a number like -0.99999. Well, if I take that -0.9 repeated and add it to 1, I'm going to get a positive number that's going to be very, very small, infinitely small, close to 0. If I divide that into a constant that's negative, all of a sudden I get something infinitely big and negative, which makes me be able to do that. Now we can say the limits as x approaches -1 in general of this function, well, that doesn't exist. Why? The left-hand limit doesn't equal the right-hand limit, and we have an asymptote. That should be known. But we're not really concerned about that right now. We're concerned about how are we behaving around a vertical asymptote. Any questions after that one? We're going to do more. Take this next one. Negative 5 over x minus 4 squared. We should know we have a vertical asymptote at 4. So we're going to look at the behavior of this function around that vertical asymptote at 4. All right. It's a little bit different in that we have this x minus 4 squared. Let's see what happens. So I'm going to just go ahead and plug in 4 from the left minus 4 squared. In my mind, I'm thinking, okay, to the left of 4, that's going to be 3.999 if I think about my number line. Well, if I take that 3.999, subtract 4, I'm going to get something that is close to 0, but negative, because 3.99 is less than 4. However, I'm going to be taking that value that's infinitely small and negative, and I'm going to be squaring it. When we square numbers, we get positives. So all of a sudden, this turns into negative 5 over infinitely small positive value, giving me something infinitely large and negative. Excuse me. So I can do this, Mr. Kavanaugh.
So because of the square on the bottom and everything inside is being squared, you know that the bottom is always going to be positive, right? Because the top is negative here, you can just disregard the numbers and find something.
Pretty much. For this example, yes. Okay? So Mr. Kavanaugh is correct. Mr. Kavanaugh says, well, if I'm just going to be squaring it anyways, isn't this always going to end up being a positive small value? Yes. And let's confirm that real quick. Negative 5 over 4 plus minus 4 squared. 4 to the right, 4.0001. Negative 5 over 4.0001 minus 4 squared. Negative 5 over something infinitely small and positive. But since it's squared, it's going to stay positive instead of switch signs, meaning that is negative infinity. Well, now we have a function which is interesting that's going to be approaching the asymptote in the same direction from both sides of it. And what's really interesting about this, while we need to make sure we do it, because what we will now be able to say, even though last unit I told you don't worry about it, it's just not going to exist, now we can say that this function, the limit at 4 in general, approaches negative infinity. Because the left-hand limit equals negative infinity and the right-hand limit equals negative infinity. But you guys should be thinking about that, and you should be saying, no, Mr. Messner, that can't be right. And why can't that be right? Because infinity is not a number. Exactly right. And since infinity is not a number, you should say, no, that's not right. We should put does not exist. Well, on the AP exam, they expect you to be able to answer both ways. And you might say, well, why can't I just stick with does not exist? Because you might have a multiple choice question, and you might not see does not exist as an option. You might see negative infinity. You might see positive infinity. You might have to get the right one. Okay, let's do another. Here's a good one to do. I'm going to show you the first one. You're going to do the second one as practice. It's an important one to show because now we have x in both the numerator and the denominator. Okay. Well, the same process is going to hold. I'm going to plug in the value. And I'm going to think of what that value is. That's very important to make sure you understand whether you're on the positive side or the negative side of our number line, because from the right and the left, they're going to look different. 4 from the left is different than negative 4 from the left. 4 from the left is 3.999, but negative 4 from the left would be negative 4.0001. So make sure we keep that in mind. Well, here's the deal. If I take 3.999 and I subtract 5, am I going to be approaching negative 1 from the left or from the right? It's kind of tough. I know this one's kind of easy to compare. I got 3.999 and 4. I know 4 is bigger, so I know this is going to be approaching a small negative value. But here, am I talking about negative 1.001 or negative 0.999? The great thing is that it doesn't matter for this other value other than 0. I can just put down negative 1 and not care about this or that. Don't care. So go ahead and write down, doesn't matter for values other than 0. Why doesn't it matter for values other than 0? Let's see if anybody can get this. Why do I not care that it's negative 1 from the left or negative 1 from the right? But I do care if it's 0 from the left and 0 from the right, Mr. Hathaway.
This is because with 0, can you positive and negative?
Exactly. Perfect. Perfect. If we think about our number line, the reason why it matters with 0 is because the sign changes depending on whether you're from the left and from the right. This is going to be a negative value. This is a positive value. But if I look at negative 1, doesn't matter from to the left and to the right. We are both having negative numbers. So I don't care that this is negative 1 from the left or from the right. I do care about that because this is still going to be a negative divided by whatever this is. In this situation, it is a negative as well, meaning this function is going to have a vertical asymptote, and to the left of it, we will be approaching positive infinity. Do that one. Make it x plus 5 on the numerator, divided by x plus 3. And that is negative 3 from the right. Now I want you all to do this, and I want you all to talk to your neighbors, and I want you all to check to make sure you're getting the right answer and you're understanding things. And if you're not understanding things, you're asking myself or your neighbors to help. All right, discuss with your neighbors. Some of you might already be on the whole skipping the thought process. Some of you really need to do the thought process and the extra steps with your number line and with everything else. Okay, we should get positive infinity. Negative 3 from the right plus 5 is 2 from the right, but I don't care. Negative 3 from the right plus 3 is 0 from the right. 2 divided by something infinitely small and positive is going to be something infinitely big and positive. This is also positive because it's a positive divided by a positive. Okay? Okay, those aren't that bad. Now, some people get tripped up when we're taking the value and squaring it. So let's be ready for two problems like these. I'm going to do the one on the left. You're going to do on the one on the right. So I got negative 2 from the left, and I'm looking at 5 over x squared minus 4. I know that there is going to be a vertical asymptote at 2 and negative 2 for this function because I can't simplify it and get rid of that x squared minus 4. Even if I factor it, I won't be able to cancel it with anything. So how is my function behaving around this vertical asymptote at negative 2? Well, let's find out. I'm going to take 5, divide it by negative 2 from the left, which is squared minus 4. Now, this is when the understanding of where your number is and what number you're dealing with is very, very important. If I have negative 2 from the left, I'm talking about negative 2.0001. If I take that value and square it, so that is negative 2.001 times itself, what I'm going to get is a number that is bigger than 4, just a little bit bigger. All of a sudden, this becomes 5 over 4 from the right minus 4. Which means, if I'm talking about 4.000 like 2, if I take negative 2.001 and multiply it by itself, subtract 4, I'm going to get something very, very close to 0 but positive, which is why this is going to approach positive infinity to the left of negative 2. And the key is this. Right there. If I take this value and square it, I'm going to get a positive value that is bigger than 4. I don't know if it's O2. It's going to be just something else. Question?
When you wrote like the positive sign, you're not making it go to the right. You're just saying it's positive, right?
This or this?
That.
This is just saying I have a number that's bigger than 4.
Okay.
Okay? It's not about how it's going. It's just about what the number is. It's a number that's really, really close to 4, but it's a little bit bigger than 4. Okay? You guys try the one on the right. Negative 2x over 9 minus x squared as x approaches 3 from the left. Before you go too quickly, make sure you understand what number you can use for a number that is to the left of 3. That's a positive 3, not a negative 3. Okay, look at what I did. Took -2 multiplied by 3, I got -6. Do not care if it's from the left or the right here, because it's just going to be negative. But here's the key. If I took a number to the left of 3 and square it, like 2.999 squared, we are going to get a number less than 9. So 8.999. Or something around that. Okay? If I take that and subtract it from 9, I'm going to get something close to 0, but it's going to be positive. That's why we get this, which is why I say this. Okay? Moving on. Let's do that, but with trig functions. You will need not just your entire unit circle, but just kind of your y-axis, your x-axis, your extremes, and you're going to need a number line. And on your unit circle, just label your extremes. Up. And on your number line, you're going to start at 0. You're going to put in pi over 2, pi, 3 pi over 2, and 2 pi. Because those are numbers too. Okay? Trying to find the limit as x approaches pi over 2 from the left of 1 over cosine of x. Well, I know that if I plugged in pi over 2 into cosine, that the cosine of pi over 2 is 0. So that means this function has a vertical asymptote at pi over 2. But the question is my function going to be approaching that asymptote in the positive direction or the negative direction to the left of pi over 2? So really the question becomes, what goes over this 0? All right, well, let's go to our number line. And let's think about what it means to be to the left of pi over 2. That's coming from 0, traveling towards pi over 2. That's right here. I'm going to just say that's pi over 2 from the left. Well, let's translate that on the number line into something on a unit circle. Well, coming from 0 going to pi over 2, if I go in a counterclockwise direction, that is coming from the left, going from smaller values to bigger values. So I'm going to say that this is where pi over 2 from the left is. Now that's, counterintuitive. If you look at pi over 2 right here, you'd think, oh, the left is over here, but that's not how you're going to think of it. You're going to think about traveling around the circle, going from 0 to pi over 2. And then you're going to remember your mnemonic for which trig function is positive in which quadrant. Well, if I think about my angles and my cosine values in the first quadrant are all positive. So like here, it's like root 2 over 2. Then here, it's 1/2. Over here is root 3 over 2. But as I notice, root 3 over 2 is bigger than root 2 over 2, which is bigger than 1/2. My cosine values, my x distances, are getting smaller and smaller. They're approaching 0. However, they are all positive values, right? So this will be approaching 0, but from the positive direction. Why? Because cosine is positive in the first quadrant, where pi over 2 from the left is located. And I'm going to write that down because it's very important. It's positive because cosine is positive in the first quadrant where pi over 2 minus is located. So this becomes positive infinity. That function to the left of pi over 2 is increasing up to positive infinity. Okay? Let's do this one. The limit as x approaches pi from the right of 1 over the sine of x. And I mean, it doesn't have to be 1. It could be 4 over. It could be anything. Okay, go do that. You can do it. Step 1 is number line. Step 2, using a unit circle. Step 3 is making sure you use the ASTC to figure out if you're talking about positive values getting closer to 0 or negative values getting closer to 0. Yep. So that tells me what trig functions are going to be positive and what quadrant. So in the first quadrant, I know my cosine values were all positive. So as you get closer in pi over 2 from the left, my cosine values are going to get closer to 0, but they're going to be coming from the positive direction. So positive values, so infinitely small but positive value. Okay? That helps me for that 0. I'm going to use that for any situation. Okay. Pi from the right. Pi from the right. Coming from 3 pi over 2 going to pi. That's coming from the right. Well, coming from 3 pi over 2 going to pi is this direction, the clockwise direction. We are right here. If we can't get that right, we're not going to get the problem right. So make sure we got that down. Just translate from a number line to the unit circle. The next step is sine values are going to be approaching 0. However, in the third quadrant, the sine values are going to be negative. From negative root 3 over 2 to negative root 2 over 2 to negative a half to very, very close to 0, but negative. So this is negative infinity. The key is that negative sign. I put that negative sign there because sine is negative in the third quadrant where pi plus pi from the right is located. One more. This one. And then we'll move on to horizontal asymptotes. I don't want you to think we're done after this one. We're just dealing with vertical asymptotes right now. Don't try to do it in your head. Check with a neighbor. That's the idea. Any questions? Now, you will see cotangent, you will see secant. Just really quickly, I'll show you this one, if it works. Nothing's working. If you have cotangent, or if you have secant, rewrite it. Oh, that's not good. Rewrite it as cosine over sine. Make sure you know what the cosine value is going to be at pi. God, everything's going so well. Oh, there we go. Pi. There we go. Okay. So here, rewrite this as cosine over sine. Now, it's important you're plugging in pi into both. The cosine of pi is -1. I don't care if it's -1 from the left or from the right. Now, the sine from pi over left, pi from the left. Pi from the left is coming from pi over 2 and going to pi. Pi from the left would be here. Sine is going to be approaching 0. However, in the second quadrant, sine is positive. We'd have 0 from the right, -infinity. Okay? That's the idea if you're dealing with like a cotangent or a secant. Just rewrite it and then deal with sine over cosine. Okay? All right. Horizontal asymptotes. Limits as x approaches positive and negative infinity. Okay, now you will be asked questions later in this course once we start reviewing things, and you are going to completely forget this fact that if you are asked to find a horizontal asymptote, you need to evaluate the limit as x approaches positive infinity and negative infinity for whatever function. I'm asking you to find the horizontal asymptote for this function. I need to evaluate this and this. They might be different for whatever this function is. Whatever. Now, how do we do this? Well, we're going to learn. And pretty much I'm just going to give you random limit as x approaches infinity questions. But you need to think of those as, oh, hey, we're finding the horizontal asymptotes for this function. Okay? There are guidelines for these. Okay? And the key to these guidelines is this fact. At the highest power term of a function, and not even within a function, the numerator and denominator is the most influential in determining a limit as infinity. We're going to be doing what we've been doing with limits, but with the concept of infinity. I'm going to be plugging in infinity in for x in these things. You might be thinking, well, that doesn't make sense. Like 2 times infinity is infinity. Infinity cubed is just infinity. How am I going to be able to differentiate? Okay. Well, here's the key. If I look at the numerator and write this situation down, I'll give you some time. So as you can find the limit as x approaches infinity of 2x cubed plus 1000x squared over 10x squared plus 5x minus 3. That's pretty much, saying, hey, find the horizontal asymptote as x is approaching, to the right of that function. Okay, that's the question. We're just already jumped to the limit part of it. Well, in the numerator, turns out if I'm plugging in infinity, this 1000x squared in the grand scheme of big numbers is useless, is like a decimal point compared to when I plug in big numbers and cube it. And I will be able to just say, I don't care about 1000x squared. That seems odd, right? 1000x squared, when I'm plugging in x's, I'm going to get big numbers. However, I'm going to get such bigger numbers when I'm plugging in to x cubed that it's not going to matter. And I'll show you. Let's say I plug in 10 to the 5th into 2x squared. So 2 times 10 to the 5th, cubed. I get a really big number. I get 2 quadrillion. Didn't even know that was what you call it. Okay, it's 16 decimals, 15 zeros. It's a big number. Well, if I plug in 10 to the 5th into my other one, 1000 times 10 to the 5th squared, I get 10 trillion, which is a big number, but it's only 14 decimal digits. Okay, this one was 16, that was 14. Well, they still are kind of comparable, but we're adding these two numbers together, and turns out the top number is 200 times the size of the bottom number. So if you think about adding something that's a 200th to something else, that is like adding 1 over 200 to 1. Is it changing it? No. We have 1.005. It's still 1. Well, guess what happens if I change this to 10 to the 10th? Let's go 100. Let's just go for it. All right. Let's see what this number. Oh, it's not. You're not even done yet. There are more zeros, I feel like. No, it says it's 3 to the. Okay, 301 decimal digits. So 301 digits, 300 zeros. This is only 204 decimal digits, which means 100. I feel like it's not big enough. Okay, this is 2 untrigatillions the size. If I divide the top one by the bottom one, turns out 2 this many times does the bottom one go into the top one. So if I take that and I put all of those zeros and add it to like 1, that's essentially what I'm going to be doing. Is it going to be changing the value? No. So when we're talking about the grand scheme of big numbers, really it's the thing that grows the fastest, that's the thing that matters. This is going to be adding a 0.2000 zeros and a 1 to whatever that value is over there. Okay, that's the grand scheme of things. So I don't care about this if I'm plugging in big values. I don't care about this if I'm plugging in big values. I don't care about that. I just care about the 2x cubed and the 10x squared. Now you can think about this 2 ways, and we need to think about it 2 ways, because for this situation you can do it algebraically. I can take the limit as x approaches infinity. Instead of having all this stuff, I can just say, well, essentially it's just like 2x cubed over 10x squared. Well, that's just like the limit as x approaches infinity of 1/5 times x. As I plug in bigger and bigger values for x, that thing's just going to continue to grow bigger and bigger and bigger, and this is going to approach infinity. So it's not going to have a horizontal asymptote. You need to be able to think about it theoretically, though. Which is just that we are growing faster in the numerator and slower in the denominator. Since I'm going faster, I'm getting bigger numbers compared to my denominator. The resultant product is going to just be bigger and bigger and bigger values. So we would say this is approaching infinity. So the guideline is if the degree of your numerator is greater than the degree of your denominator, you're going to trend towards positive or negative infinity. There's guideline number 1. Now, signs do matter, positive or negative infinity. Be careful with your signs. Here's the limit as x approaches negative infinity. 4x cubed minus 20x over 1000x squared plus x. Again, when we plug in bigger and bigger numbers, the higher degree term is going to really outweigh the lower degree term. So it's like adding a decimal point with 1,000 zeros followed by a 1 to 1. And watch this, if I'm plugging in negative infinity, after I simplify this, well, that negative infinity times the 4 over 1,000, that's going to approach a huge negative value. So you need to be careful with your signs if your degree of your numerator is bigger than the degree of your denominator. You could also think about it if you plug in a big value into your numerator and you're cubing it, that's going to be a faster growing negative value. If you plug in a big negative value into your denominator and you are squaring it, that is going to be a slower growing positive number. A negative divided by a positive will give you that negative. Next situation. If the degree of your denominator is greater than the degree of your numerator. What happens if I take a value like 5 and I divide it by a ever-growing huge number? Like 5 divided by 10 quadrillion. What am I going to get? Something that's really what? Small, close to 0. Well, if it keeps getting bigger and bigger and bigger in the denominator, I'm going to get smaller and smaller and smaller as a product. This is going to just pretty much trend towards 0. I'm going to just say it's essentially equal to 0. Because it's like a quadrillion zeros and then a 1. Pretty much 0. Well, if I looked at this situation, I want to find the horizontal asymptote of negative 5x to the 4th plus 20 over 2x to the 5th. First thing I can do is just get rid of the 20. I don't care about that. And this would be the algebraic way to do it. I'd have negative 5x to the 4th over 2x to the 5th. The x's would cancel. I'd have negative 5 over 2x. If I plug infinity into that x, my denominator was growing. I'd have negative 5 over something infinitely huge. We'd get something infinitely small, essentially 0. Now, we would say that this is essentially 0, but it'd be coming from the negative side. In this situation, we don't care. We just say the horizontal asymptote is located at 0. Now, theoretically, and this is important because we will not be dealing with things that we can simplify algebraically, we say if we are growing slower in the numerator than our denominator, the resultant would be a fraction that would get smaller and smaller and smaller, and it essentially trend towards 0. Okay, so degree of your denominator or the growth of your denominator is faster than the growth of your numerator, 0. You don't have to necessarily say degree, you could say growth is greater than the growth. Okay, now the last situation is if your growth is the same. If the growth of your numerator and the growth of your denominator are the same. Well, the best way to show this is the algebraic way. You got negative 4x cubed plus 2x minus 5 over x cubed minus 1. You should know that all the stuff to the right of those x cubes, insignificant. Don't care, don't care, don't care. It's just this. And watch what happens. The growth of the numerator and denominator, since they are essentially the same, they will cancel each other out. And you will end up with just the coefficients of your highest degree terms. Do you need to be careful with signs? No. If I plugged in negative infinity, guess what? That negative would cancel with this negative. What would you have? Just negative 4 over 2 in this situation, which is just negative 2. The other stuff doesn't matter. The x cubes will cancel. That is what we think about when we're dealing with huge numbers being plugged in for x. We might see square roots. Well, with square roots, you need to be careful about your signs. Okay? Here's how we're going to treat it. Just write down this one. Limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. Well, the negative 2 won't matter in the numerator, and the plus 1 won't matter in the denominator. So algebraically, you can rewrite it as this. Well, after I rewrite it like that, I have a product under a square root. I could rewrite that as root 2, and then the square root of x squared is going to be x. However, the square root of something squared could be positive or negative. The x's will cancel, and your answer will be 3 over root 2. However, you need to check to make sure it's positive 3 over root 2. If I plug in a positive value, the numerator would be positive. The denominator will always be positive because I'm squaring it and then taking the square root. So this is good. This is positive. But same question, just changing the positive to a negative, this would turn into negative 3 over root 2 as an answer, because we'd have a negative numerator divided by a positive denominator. So in this situation, that function with that square root actually has 2 horizontal asymptotes. It'll have a horizontal asymptote at 3 over root 2 and another horizontal asymptote at negative 3 over root 2. Two more big things to go through. We only have 2 minutes. Okay, so you're going to get through this first thing, and then you have to watch the second thing. This first thing is dealing with trig functions as we're plugging in infinity. The key to plugging in larger and larger and larger values into a trig function like sine or cosine is that it doesn't grow. It just oscillates. It will go up to a max value of 1, and it'll go down to a minimum value of negative 1. And it'll be in between the entire time. So you treat it almost like a constant. Look at this one. If I plugged in infinity into sine x over x, sine x is just going to oscillate between negative 1 and 1, small values. But the denominator is going to continue to grow. So that limit is equal to what? 0. All right. Watch the rest online. Have a good weekend. So that's the key concept. This does not grow. This is almost like a constant going up to 1 down to -1, but this will grow. This will reach 0. So let's look at this problem. Limit as x approaches infinity of the cosine of 1 over x. Well, let's think about it. If I plug in infinity, the denominator is going to grow. The numerator is going to stay constant. This is going to approach 0. So this is almost like asking me what the cosine of 0 is. Well, cosine of 0 is 1, therefore this must be 1. Here, if I plug in infinity to sine, it doesn't matter that it's squared. This is just going to increase and decrease, okay? And it's going to be positive and negative values as we're continuing to go. And then this will continue to increase. So what we're going to end up happening, and this is an interesting situation, this will trend towards both positive infinity and negative infinity. It's a little bit complex of a problem, but the key to the concept is that sine is not growing. It's just oscillating. Okay? Sine does not grow. Cosine does not grow. It just oscillates. Okay, now let's go to more of the theoretical side. We've been dealing with powers, x to a power, like x cubed. Okay, and other things, 2x squared, 10x squared, everything where it's just a variable to a power. Well, we might have to deal with horizontal asymptotes with variable powers, so like a number 2x, or we might have to deal with like log x or e to the x, okay, which is just a number to a power. And the question is, what's going to grow faster, x cubed or 3 to the x? Well, you think about it, you plug in a value like 1,000. 1,000 cubed is going to be a big number. Let's check this out. If I take 1,000 and cube it, big number, 1 billion. Well, let's take three to the thousandth. Okay, that's a big number, 478 digits. This is what 3 to the thousandth is, okay? So obviously, that if we're only plugging in 1,000, which is a small value, I'm only plugging in a small value in the relative scheme of big values, okay? It's obvious this is going to grow faster, okay? So it turns out a number to a power is going to grow much, much faster than a variable to any number. This could be a 10,000, eventually 3 to the power will be faster, will be a bigger number than x to any number. And this is why this will grow faster. Then if you compare different values, obviously the 4 to the x is going to grow faster than 3 to the x. So this is very, very powerful. And then if you think about e to the x, it's important to know that e is just a number. It's 2.7178, So e to the x is going to be slower growing than 3 to the x, okay, but faster growing than 2 to the x. And obviously faster than x to any power. Now, what about log x? So e to the x is growing faster. Well, how does log grow? Well, it's important to remember that e and log are inverses of each other. If I take the log of e to the x, I just get x. And if e to the x grows exponentially fast like this, log is going to be growing exponentially slowly. So in terms of growth, of expressions, sure, the slowest is going to be just a number, like 5. 5 doesn't grow at all. This is no growth. But then's going to come your log to the x. Then's going to come x to your numbers. And then will come your numbers to the x. Okay? Slowest all the way to the fastest. And this is important because you will have questions like these, where there's no algebraic way to tackle this problem, to tackle these problems. The limit as x approaches infinity of x to the 99th over log x, or log x over e to the x, or e to the x over x to the 99th. I can't cancel things. So I have to take it about the theoretical way to do things. The theoretical way is thinking about the rate of growth. Well, log x is actually the slowest out of all of these. So this is going to be slower over under faster, and we know that if we're growing faster in our numerator than our denominator, like our degree being bigger in the numerator than the denominator, this is going to trend towards infinity. Okay? Careful about our signs, but with positive infinity. Now here, this is going to be growing slower than e to the x. When we have something growing faster in the denominator, this is going to trend towards 0. And our last one, e to the x, this is going to be faster than x to any number. So this is going to also trend towards infinity. So which one equals 0? Our middle guy. Okay, so that's kind of talking about the rate at which things grow. No growth to fastest growth. But one thing we do have to need to be careful about, and maybe before we do that, we'll do this one really quickly. So I have x to the 99th and 2 and 3 to the x. Actually, 3 to the x is going to win. I don't care about x to the 99th and 2. Here, e to the x and 1000x squared. Don't care about that. Which one grows faster? Well, 3 to the x. 3 is a bigger number than 2.718. This will grow faster. Since we're going faster in the numerator than the denominator, this is going to trend towards infinity. Okay? Good example problem. But here's what's really, really important. And if you're watching this video, I'm very, very glad that you're watching this video, because you're going to understand this and you're never going to make this mistake on a quiz or on future test questions. And that is, does sign matter when you have a number to a variable power? Let's think about it. If I plug in bigger and bigger values in for x that are positive, 3 to that bigger value, that infinity, that's going to be some huge value. But what if I plug in bigger and bigger negative values into x? Is this going to be also infinity? Is it going to be negative infinity? Well, let's think about it. Let me fix this infinity first. If I'm plugging in a big value, let's say that's negative 1,000. Well, what's 3 to the negative 1,000? That could be rewritten as 1 over 3 to the 1,000th. Or I could go 3 to the negative infinity can be rewritten as 1 over 3 to the infinity. That's one of your exponent rules, that if you have a number to a negative power, it's the same as 1 over the number to the positive power. It's one of those exponent rules from algebra. Okay? Well, it still applies with infinities. I can go from 3 to the negative infinity to 1 over 3 to the infinity. Well, now I have a constant in my numerator. My denominator is going to grow faster and faster and faster. This is going to approach 0. So all of a sudden, this matters. And actually, these can be seen on the graph of any, number to a variable power, like e to the x. Well, if I go to the right, my function increases. And the limit as x approaches positive infinity is infinity. But if I go to the left on my x-axis, what is e to the x doing? It's getting closer and closer to 0. Okay, so sign does matter with numbers to a variable power. If I get a question like this, the limit as x approaches negative infinity of e to the x times x to the 10th. Well, what I'm going to be thinking is I'm plugging in negative infinity, and this could be rewritten as like x to the 10th over, or infinity to the 10th over e to the infinity, because it's e to the negative infinity, and we should know that e to the power is going to grow faster than x to any power, therefore this is equal to 0. Even though you don't even see a denominator to begin with, and you think, oh, we're just going to be going faster and faster and faster, It is different when we're dealing with variables in our power when we're dealing with variables in our power and negative numbers, okay? So be very, very careful with that in the future. Thank you for watching the rest of this video.